Today we are going to prove that the derivative of sin x is cos x. And how are we going to do that? We are going to do that by using the definition of the derivative. So the definition of derivative is, if you have a function and here the function is sin x, so y is equal to sin x. Y can also be called f of x because it is a function of x. So according to the definition of the derivative, if you have a function f of x, the derivative is limit h approaches 0 of f of x plus h minus f of x over h. So firstly you need to write f of x plus h, and that means that you need to replace x with x plus h in the function, and here the function is sin of x, so this becomes sin of x plus h as I have written. So sin of x plus h minus f of x, which is just sin x, so sin of x divided uh, by h, and we are taking limit of this expression, uh, and we are saying that h is approaching 0. So this is basically the definition of the derivative, and this definition can be used to find the derivative of any function, and here we are using this to find the derivative of sin x. So you can see that in the numerator we have sin of x plus h. So sin of x plus h, uh, we will use a formula to expand this. So the formula is sin of alpha plus beta is equal to sin of alpha cos of beta plus cos of alpha sin of beta. So here alpha is x and beta is h. So in the numerator it will become sin of x into cos of h plus cos of x into sin of h, minus sin x will remain as it is in the numerator divided by h, and we are taking the limit, and h is approaching 0. So our derivative f dash of x will be equal to limit h approaches 0. So now we can see that in the numerator we have three terms, and two of those terms have sin x in them, so we can separate those terms. So I have separated those terms, sin x cos h and minus sin x. I have written them separately, and I have written cos x sin h term separately. So this becomes limit h approaches 0 of cos of x sin of h over h plus sin x cos h minus sin x over h. So you can write this, there's no issue, because if you even combine these two fractions you get the same fraction written in the above. So now we'll use a property of limits which states that the limit of a product of two functions is equal to the product of the individual limits of those functions. So we have cos x sin h over h here, the first term. So I'll write this as, firstly, I'm using the property that the limit of the sum of two functions is basically the sum of limits of those two functions. So there are two terms here, cos x sin h over h plus sin x cos h minus sin x over h. So I am separating the limits on those two expressions. So this becomes limit h approaches 0 cos x sin h over h plus limit h approaches 0 sin x cos h minus sin x over h. Now using the property which I was telling you about a few moments ago. So we have a product cos x into sin h over h, and I am separating the limit on both of these functions. So I am separating sin h over h, and I'm from cos x. So this will become limit h approaches 0 sin h over h into limit cos x and h is approaching 0. Similarly, the second limit can be written as limit h approaches 0. Um Sin x is basically common in the numerator, so sin x will be taken common, and we'll have sin x into cos h minus 1 over h. So if you look at this particular limit, limit h approaches 0 sin h over h, so this is equal to 1, and I've made a video about this also, but h needs to be in radian here. um, for radians I proved that this limit is equal to 1. The angle must be in radians, not in degrees. So in the first term we have 1 into uh, we are taking limit of cos x as h is approaching 0. So cos x is basically a function of x, and we are taking limit with respect to h. So we don't have any h here, it is a function of x. So cos x will remain cos x. We can't really put h is equal to 0 here. So 1 into cos x will be cos x, plus we have the limit h approaches 0, and the same property which we used earlier will be used here again. um, will separate the limit on sin x and cos h minus 1 over h. So this will become cos x plus limit of sin x, h will be approaching 0, into limit h approaches 0 of cos h minus 1 over h. So again, um, we have a limit in which h is approaching 0, but the function written is sin x, not sin h. So there is no h in the function, so we can ignore this limit and write sin x as it is, because it will make absolutely no difference. So this will become cos x plus sin x into limit of cos h minus 1 over h, and h is approaching 0. So the only limit left now is this limit. We need to find this limit to find the derivative of our function, which was sin x. So we have to find the limit of cos h minus 1 over h, and h is approaching 0. So firstly we try putting 0 in this expression. So if we put 0 in this expression, we get cos of 0 minus 1 over 0. Cos of 0 is simply 1, so 1 minus 1 is 0, and in the denominator we already have 0. So we are getting 0 over 0 form, which is an indeterminate form. It is not equal to any value. So we need to get rid of this 0 by 0 form in order to find this limit. So the main problem lies with this denominator h. We need to get rid of this, so because in the denominator we can't afford a 0. So what can we do to get rid of this indeterminate form? So in the numerator we have two terms, and whenever we have two terms in a limit, we can actually try using rationalization for those kind of limits. So we can try multiplying and dividing by cos h plus 1. This is basically called rationalization. So when we rationalize this becomes limit of h approaches 0, uh, cos h minus 1 over h into cos h plus 1 over cos h plus 1. So in the numerator we are getting a minus b into a plus b form, so which is equal to a square minus b square. So cos h whole squared minus 1 whole squared. In the denominator, the denominators will be multiplied, so they will become h into cos h plus 1. So in the numerator we get cos square h minus 1, and cos square h minus 1 is basically sin square h. I've written here that sin square x plus cos square x is equal to 1. This is an identity, and here if you want to find the value of cos square x, you need to move this this sin square x to the other side, and this plus 1 sorry, we need to find we want to find the value of cos square x minus 1. So we need to move this plus 1 to the left hand side. We are left with cos square x minus 1, and we want its value, so we need to move this plus sine square x to the other side. This will become minus sine square x. So cos square x minus 1 is just minus sine square x, and we are left with limit h approaches 0 minus sine square h over h into cos h plus 1. And in the numerator, we can actually write this as minus sine h into sine h. Simple. A into a is a square, and there was a minus sign. So minus sine h into sine h over h into cos h plus 1. So again, we want to use the product property of limits, so we'll separate sine h over h, and this is basically helpful for us because sine h over h, we know a limit. Whenever h is approaching 0, sine h over h approaches 1. So that's why we are separating this. So limit h approaches 0 minus sine h over h into sine h over cos h plus 1. So no difference, it is exactly the same expression. So we'll separate the limit on both of these expressions. So because they are being multiplied, so the individual limits can also be multiplied. So limit h approaches 0 minus sine h over h into limit h approaches 0 sine h over cos h plus 1. So we are left with the first limit is basically, you can take this negative sign out, and this will become limit of sine h over h approaches 0, which is equal to 1. And the second limit is limit h approaches 0 sine h over cos h plus 1. So we don't have any issues with this second limit, because if you put 0 in this limit, you don't get an indeterminate form or 0 in the denominator. So we just put the value h is equal to 0 in this limit. So we are left with negative 1 times sine of 0 over cos 0 plus 1. So the limit becomes negative times, we had sine 0, which is 0, over cos 0, which is 1. So 1 plus 1 in the denominator. So this will be equal to negative 1 times 0 over 2, and 0 divided by anything is equal to 0. So this will become 0 times minus 1, and 0 multiplied by anything is equal to 0. 0 times minus 1 is 0. So we found our limit which we require to find the derivative of our function sin x. So the limit was cos of h minus 1 over h, and h was approaching 0. So this is equal to 0. We have found it. So now we'll be putting this value in the equation of our derivative, and we'll get our derivative. So f dash of x is equal to cos x plus sin x into 0, and anything multiplied by 0 is just 0. So cos x plus 0, and cos x plus 0 is simply cos x. So we have proved that the derivative of sin x is simply cos x.